So let's look at case 2 here, where we multiply together a normal number with a normal number and get a subnormal number. Now we're going to go through the examples here where the most significant bits here are 0, 0, 0, 1, 1, 0 and 1, 1. Now it turns out in this case we only actually have 2 to look at. So let's first of all look at the values of 0 and 1. So an example of this would be 1e to the minus 21 times 1e to the minus 21, which gives us 1e to the minus 42. So I've put those into the little tool here, and you can see that both of these are normal numbers, but when we multiply them together we're going to get this number here, which is a subnormal number. So we know that in a subnormal number the exponent is going to be all zeros. But in this case here, if we were to look at the two values here, we would have xe is 57 minus the 127 gives us minus 70, and the ye is exactly the same. So we'll have minus 70 plus minus 70 is minus 140, plus the 127 gives us minus 13. The minus 13 isn't 0. So we can't use this root here in order to determine if we've actually got all zeros here. We have to have some other method of ensuring that we get all zeros in the exponent. Now, one of the ways of doing this is to extend the exponent by 1 bit. And before we do the multiplication, actually normalize the subnormal number. But we'll get into the details of doing that whenever we look at the actual implementation of this in a float point unit. There's a couple of different ways that we can do this. So let's continue with the example here. So let's assume that we've found a method of ensuring we've got all zeros in the exponent, and we'll do that whenever we come to look at the actual implementation in logic. Now let's look at the actual mantissa here. Now this is the correct result here. So let's count the number of zeros. We're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros. And after the 13 zeros we're going to have a 1, 0, 1, 1. Now the 1, 0, 1, 1 is just the 1, 0, 1, 1 here from our multiplication of our mantissas. Now the problem with this thing here is that it isn't in the right position. We're going to have 13 leading zeros for this. Also, remember that the decimal point actually starts at this point here. So the question is, how far along to the left are we going to have to shift the decimal point in order to get it in the correct position? Well, we're going to have to shift it one value to this point here. So in effect that would be a normalizing shift. This would be ensuring that the first digit here is in effect a 0, because when you normalize a subnormal number, the first digit will have to be a 0. So that would be a normalizing shift here. But then you would have to have another 13 zeros added on as well. So we'd have to move the decimal point 14 places in all. So how are we going to generate that number of 14? Well, we generate that number of 14 from the difference between the exponent values. So if we have here our exponent value for x and exponent value for y, we're going to have minus 57 plus the 1, we're going to have 57 minus the 127, which gives us a minus 70, and the same for the y value because they're both the same here. Whenever we add them together we get minus 140, and then we add the 127 gives us minus 13. So minus 13 is not far out. The minus 13 actually gives us our number of zeros. But of course if we're starting from this point here, in order to normalise it, we're going to have to move it one more. So we could see that we could add in an extra value of 1. So we had a value of minus 14. So this is going to give us our shift in order to ensure that we're actually sitting with the mantissa in the correct position. Now we don't need to bother for the moment with the values of the negatives and the positives, shifting the point left and right, and which one will shift it one way and which one shifts it another. We can deal with that in the hardware implementation. Also we can deal with where we actually start the decimal point. So we could, instead of having a decimal point here, we could start everything from this point here and just work from this point within the logic. Again, we'll get to that whenever we come to designing the full implementation in the logic. So let's run it up in the tool and we'll have a look at it live in the tool. So that's us live in the tool now, so we can put in our 1e to the minus 21. I'll just copy this and paste it in for speed. So that's our two results, that's our final answer here. And you can see that we have our output here, which is the multiplication of these two mantissa values, and we have our 0 and we have our 1 at the most significant bits of this multiplication. So you can see here then that if our decimal point was originally sitting from this here, our decimal point is sitting at this point here, which is between the first 1 and 0, then the decimal point would be sitting in effect at this point here. So we would have to have shifted it, well, one place here and then the other 13. So that would have been 14 places to get the decimal point back up to this point here. Now there's one other interesting thing to note in this example here, and that is the issue of rounding. So it's rather awkward to explain this, but we'll try our best here and see if we can get an explanation of the rounding. If you were to look at the number here, which is the mantissa, well, this is nothing other than the 1011, and this is the 1011 here. So let's continue and looking along with this number. We've got 1011, then there's 00, which is these two bits here, and then we're going to have a 1, which is this bit, and the next bit, the last three bits, are going to be the value of our 010. But the last three bits we've got here aren't 010. The last three bits are 001. So there's been a change made somewhere along the line, and the change that's been made is in rounding the final result. Now we've rounded the final result because the very next bit after this here is a guard bit, and that's a value of 1. So this bit here is none other than the bit here is the guard bit. So we know the guard bit's going to be a value of 1. Now there's other two bits which I've shown here. So the other bit here is actually the round bit, and we've created the round bit by ORing together the other 8 bits here. So I've picked 8 bits in this instance. I'm not sure exactly how many bits would be actually chosen in a proper floating point unit. I've not been able to find that information out, so if I do, I'll get that information to you. But I've chosen 8 bits, and when I've ORed them together, as long as at least one of them is high, then we know we're not going to have any problems with having values that are in an in-between state, right at the very middle between a positive and a negative value. So it means that this value here, if at least one of them is high, then we're going to get a result, a high result. And when you get a high result here, we put our low result into the rounding bit. So the rounding bit then becomes 0. But we have to lift this 1 here now over into the next position. So that's what we've done here. This 1 here has gone into this position here, so that has become a 0. And then this 1 here has gone into that position, and that has become a 1. So now we have, instead of having 001 in the last 3 digits, we've now got 010, and this is the rounding that's been taking effect here. So rather awkward to explain that, and if you're not sure, you can always get in contact with me and I can get into it in more detail. So that's us actually almost finished now. If we were to look at the possibility of having a 1 and a 0 here, then an example of that would be 1e to the minus 20. So if we change this to 1e to the minus 20, 1e to the minus 20, you see here we've now got a 1 and a 0. In this case here, the correct answer is going to have 1, 2, 3, 4, 5, 6 zeros. So that's 6 leading zeros, and we're going to have a 1 and a 0 here. So the original decimal point is going to be at this point here. So we're going to have to move over 1 and 2 and then another 6 in order to get to the right position for the mantissa. So we're going to have to shift the decimal point 8 positions. So the decimal point originally sitting at this point here. So in effect this is the 1 and the 0. This is the first 1 and the 0, and that's the decimal point there. So you can think about the decimal point as being at this point here, and we've shifted it 1, 2, 3, 4, 5, 6, 7, 8. And again you can see here that working through the exact same process with the exponent difference is going to give us a value of -7. We take 1 away, we'll get a value of -8. So again we're able to find that position here in that instance. Now if we were to have a value of 1, 1, then we would do exactly the same here as well, and it would shift it that correct number of positions. And the value of 0, 0 doesn't occur. So that covers all of the possibilities here now of multiplying a normal number with a normal number and getting a subnormal number. So thank you for listening. I'll get you on the next video. Goodbye.